So the next thing we're gonna do is we're gonna keep pretty much everything the same, except we're gonna change where we put an object. So I gotta go to the next page. I'm gonna write another example. And we're gonna talk about the same lens. So it's the converging lens with focal length equal to 20 centimeters. Okay, so it's the same lens as what we had in the previous page. But now we're gonna move where we put an object. So we're gonna put an object, 10 centimeter away from the lens. So SO now is going to be 10 centimeters, right? So the one before is SO equal to 40. Now we're going to reduce it to 10. Okay, and we want to find where the image is. Where is the image in this case? Let's do the ray diagram first. So ray tracing. Again, first we start with drawing the optical axis, the line that guides everything. Next, we're gonna draw the lens, which is here. Okay. F again equal to 20 centimeter, like this. Now we need probably to zoom in a little bit. So I'm gonna draw with a different grid scaling. Okay. So one grid here gonna be equal to 5 centimeters. Right, so it's just different scaling to make things a little bit easier to draw. So the converging lens has a focal length of 20 centimeters. That's 4 grids. So I can mark first that my focal point is going to be 1, 2, 3, 4 here, and 1, 2, 3, 4 on the other side, which is there. So this is these 2 points are my focal point for this lens. Now an object is at 10 centimeters away. So the object is somewhere here. That's my object. Okay, 10 centimeters away, 2 grids, because each grid is 5 centimeters. Okay, now we are ready to draw. So first, the line is, we're gonna follow what we did here. We're gonna draw the blue line, which is the one parallel to the horizontal line. So that's the one going this way. And this one gonna get bended towards the focal point on the right hand side. So the light gonna go this way. It's a little bit hard to draw. Something like this. Okay, so to the best of my ability, that's how the light ray looks like. So it's gonna go to the right like this. It's gonna get bended towards the center like this. Okay, so that's the first line. The second line, going back, we're gonna draw the red one. The red one is gonna go straight to the center of the lens. So it's not gonna get any change in terms of the direction. So the red one gonna go straight like this. Oops, got something like this. Maybe a little bit to the left. Something like this, okay? Again, going straight to the center of the lens and then go through without any change in the direction. So you can see something different here. Those 2 lines, the blue one and the red one, they don't intersect at the right hand side of the lens. So it's really strange because when they don't intersect, you cannot say where the image is going to be. Because remember, going back to here, we know that the tip of the image is here because those are, that's the point where those two lines intersect each other. But it's not the case here. So what do we do? Well, the thing is that if we somehow stand here and look at these two light rays coming towards you, imagine the situation that we talked about earlier. So let me get back a few pages here, right? So the eye doesn't care where exactly the light comes from. It only cares about the light coming straight to the eyes. And it's kind of think that the light coming straight is coming from the object somewhere behind. That's happening here also, right? Even though the light ray does not intersect, but what you can do is you can, or the brain get fooled by thinking that, oh, the way light traveling is probably because there's an object somewhere behind here that is giving out the light in such configuration, something like this. So we need to backtrack the light direction like this. Okay, so our brain thinks that there's an image here. So I need to draw it carefully. There's an image here, right? Because that's how the light enters the eye is going to look like to our brain, right? Even though the light does not really intersect, so it's as if there's an actual image there giving out the light in this fashion. Okay, so because the light ray does not actually intersect each other, the image here, which is not real, right? Because it's something that the brain kind of construct, the brain imagine it. This is what we call virtual image. It's a nice way of saying that this image is fake, it's not real. Okay, but we don't want to use that strong word here. So we're going to call it virtual image, right? So the virtual image is the image where the brain imagines. So it's as if the image is there giving out the light, something like this. So another way of putting is that is the image where you need to backtrack the light ray, and the backtracking gives you some intersection here. That's what we call virtual image. It's not real. It's not like what we have here. This is really the two or more than two lights intersect at this point. This is what we call real image. Because light ray really converge at that point. This is not that. This is what we call virtual image. Okay, so it's not really there, but your brain imagine that the image is there. Right? So that's what we call a virtual image. So what we see here is that if we put an object closer than the focal length of the lens, right? The focal length of the lens is 20, but in this case, the object is 10 centimeter away, right? So if SO is less than the focal length F, then you're gonna get virtual image. And this is one example here, right? So this is what the ray tracing gives us. So let's confirm this with the lens equation. I'm gonna erase this person here. So the lens equation is the same equation that we had before. 1 over f equal to 1 over SO, the object distance, plus 1 over SI, the image distance. 1 over f is the same as before. It's 1 over 20. 1 over SO is 1 over 10. And then plus 1 over SI. Okay? Now you have to be a little bit careful with solving this. 1 over SI is 1 over 20 minus 1 over 10. Okay. So in order to solve this, you're gonna have to do some kind of, arithmetics, and you get minus 1 over 20. So SI equal to minus 20 centimeters. So that means two things. First, the image is virtual. And how do you know it's virtual? Because of the minus sign here. Okay, so minus sign here, minus sign says indicates that the image is virtual. So we have virtual image. If we have positive SI, then it's going to be real image. Okay, so it's virtual image. It's negative. And it's 20 centimeters away from the lens. So 20 centimeters is about 4 grids. So it's actually it should be somewhere here, right? But again, because of our imperfection in the drawing, it's not exactly what we have, but it's good enough, it's close enough. Okay, so the ray tracing again give the general guideline of what should be the image position, but the accurate calculation comes from lens equation, and that's what we did here. So that's the interpretation of this minus 20 for SI. Again, minus means it's virtual image. 20 is 20 centimeters away from the lens. And because of the image being virtual, the image and the object are on the same side as of the lens, which is the left-hand side in this case. Okay, so the virtual image is always on the same side as the object relative to the lens. And not only that, the image is, upright instead of upside down here. So that's another thing that we can say generally. So let me kind of summarize here, is that SI larger than 0, that means the image is real image. And image different side of the lens, this is compared to the object, and it's upside down. Okay, if SI is less than 0, which is what we have in this page, we have virtual image. Same side, okay, same side as the object, and the image is upright instead of upside down. Okay, so everything is opposite, right? And this is what the minus sign tells you here. Okay, so if you solve this kind of equation, lens equation, and you get negative SI, then you can say these three things about the image, right? It's virtual, it's on the same side as the object, and it's upright instead of upside down. If you get SI to be positive, then it's going to be real image. It's going to be the opposite side of the lens. So the object is on the left-hand side, then the image will be on the right-hand side, and the image will be upside down. Okay, so that's what we have here. All right, so far so good. So for this kind of lens, which is converging lens, these two cases are what you're gonna get, right? So it's not gonna be any more complicated than this. But things will be more complicated if we talk about a different kind of lens. So that's what we're gonna do here. Okay, I have this kind of like small diagram to kind of explain what we mean by virtual image. So again, this is kind of what we had before, is the light entering the eyes and then, appearing on the retina is coming from this line, but it's as if the image is there, where in reality it's not there. Okay, and this can be useful, you can see, because it makes the object larger, right? The image is larger than the object, so you can see things better. This is how a simple magnifying glass works. Okay, so an object is get magnified up by creating a virtual image here, so you can see things to be larger. All right, let's talk about the other type of lens, which is called diverging lens or concave lens. As the name suggests, it's the lens where the light ray gonna diverge away from the parallel ray. So we have again three cases here. Not three cases, like three properties. If the light ray coming from the left hand side is parallel like this, the light gonna get bent away, hence the name diverging lens. But it's gonna bend away such that if you backtrack each line, they're gonna meet at a single point. This is the meaning of the focal point of this diverging lens or concave lens. Okay, so it's gonna diverge the light away. So if you backtrack, they're gonna meet at one point like this. On the other hand, if you have the light coming in kind of like in converging way like this, right? And it's converging to a single point here, right? So if you put the lens such that this point is exactly the focal point of the lens, the light coming out will be parallel, like this. Again, this diagram is just this diagram running in reverse. So there's nothing too fancy here, okay? So light going parallel gonna diverge out. Light converging gonna become parallel if the direction is such that it's pointing towards the focal point of the lens. And the last thing is the same as before. If you have the light ray going towards the center of the lens, then it's not gonna have any effect on that particular light. So it's the same thing. Okay. One thing that I will say now, and we're gonna see this again when we talk about lens equation, is that the diverging lens or concave lens use the focal length to be negative number. For example, minus 20 centimeters, okay, instead of positive. So this negative number in the focal length, this one indicate that it's a diverging lens. Okay, so again, a single number of the lens gonna tell everything that you need to know for the lens itself. So now let's just see how we draw the ray diagram again. So I'm gonna go to the next page. I'm gonna have an example. In this case, we're gonna have diverging lens. And let's say the focal length is minus, let's just call it minus 20 centimeters, like this. Okay, and let's say we put an object at the distance which is 40 centimeters away from the lens. Where is the image? Again, we're gonna start with ray tracing diagram. So first thing we do is to draw the optical axis, a nice horizontal line that guides everything here. And we're gonna put the lens somewhere in the middle, let's say here. So it's the diverging lens, so we better draw it like this. Okay, so a diverging lens is thinness at the center of the lens, which is opposite of the converging lens that we had before. Now, let's just make one grid equal to 10 centimeter. So that means my focal point of this lens is going to be this point and this point here. Just putting there to help with the drawing in a few seconds. Okay, and let's just say F equal minus 20 centimeters. Okay, the minus sign is not that important when we do the ray tracing. It's important when we do the lens equation, but we're gonna put it here anyway. All right, next thing we're gonna put in the object. So the object is 40 centimeters away from the lens, so it's gonna be here. So this is the object. Okay, 4 grids away from the lens. So let's draw the ray then. The first thing, again, always is to draw the line which is parallel to the horizontal line. So I'm going to start by drawing this line here, going like this. This is a converging lens. So what's going to happen? Well, let's go back and look at how the light behaves in this case. Light going parallel gonna get diverged, but it's gonna get diverged such that it backtracks to the focal point here. So that means the light gonna go this way, right? But it's gonna go that way so that when you trace back, it has to intersect that point. So I have to be a little bit more careful in drawing this. And I probably need to draw it this way. Try one more time this way. Okay, so light gonna go that way, and I hope, well, to the best of my ability, that this line, when tracing back, it's gonna intersect that focal point here. So that's our first line. The second line is, again, is the line going through the center of the lens, which will not change the direction. So the second line is going to be the line that go through the center of the lens like this. Here. Okay. Going through the center of the lens, no change in the direction. So we have these two lines, two rays. And again, this is kind of similar to what we had in the previous case where the line don't really intersect. It's only when you backtrack one of the lines so that you have intersection. Exactly what we have here. Like these two lines, they don't intersect. But this line is intersecting with this dashed line, which is the backtracking. So again, this is the case where you have the virtual image. Because by looking, so imagine there's an eye here, maybe a really big one like this, right? Looking at the direction of the light ray, it's as if the light coming from the image which is here. Again, it's not the real image because it's something that your brain needs to imagine happening, right? There's no really intersection between the blue one and the red one, right? It's the blue one tracing back here, so you get an intersection. So this is another virtual image. So this is the image. This is the object. This is again a virtual image because it's not real. And not only that, it follows everything that we knew before. It's on the same side as the object. it also upright instead of upside down. So it's perfectly a valid virtual image that we are used to. So we can imagine that if we run the lens equation, we should get Si to be something like negative number. So let's confirm that. So the lens equation, again, 1 over f equal to 1 over So plus 1 over Si. Now be careful here, very careful that f is negative. So you have to put in negative number in this equation for f. This is where the negative sign comes from. Okay, so f is negative, so it's 1 over negative 20 equal to the object distance, which is 40. The object distance is always positive because that's kind of, given by the problem. Okay, so it's always positive 40. And then we need to solve for Si. Okay, so this is what we have. So let's try to solve this. So 1 over Si is minus 1 over 20 minus 1 over 40 like this. Okay, so solving this might be a little bit tricky, so you have to be a little bit careful. So you can do this. Minus 1 over 20 is minus 2 over 40. So it's actually minus 3 over 40. So Si is actually minus 40 over 3, which is about minus 13.3 centimeters. Again, it's a minus sign. That's what we expect, because we know from our ray tracing that it should be a virtual image. So virtual image should give you negative sign here. Okay, so it's negative sign, and so it's virtual image, and it's 13.3 centimeter away from the lens. It's a virtual image, so it's on the same side as the object, and that's exactly what we have here. 13.3 centimeter is about 1 and 1/3 of a grid. And that's exactly what we have here, right? The distance here is 1 grid here and about 1/3 of the grid. So we are pretty accurate in this case. So the ray tracing is not bad at all. But in other words, in any case, we use the lens equation to confirm with the accurate number. Okay, so this is what we have. And you're going to see that the the diverging lens, which is what we have here, always going to give virtual image. Okay, no matter where you put the object. So in a sense, in terms of calculation of like how you think about this, the diverging lens is a little bit simpler because the case that you need to think about is actually more limited compared to a converging lens. But if you understand how the ray tracing works, then it's going to be as simple as the one that we deal with before. Okay? So again, just look through this example again and then try to understand every single step, okay? How I draw this image and how I solve for this one. All right? There are two more things that we need to talk about, which is two different kind of curve mirrors. And good news is that in terms of physical understanding, it's actually very similar to these two types of lens that we just talked about. So in terms of like, it's two more things, but it's not really two more things, right? So we're probably gonna talk about that on Monday, right? Because I don't have enough time to cover that. But before we finish, let's talk a little bit about what we call the magnification of the image. So you can see here, in this particular case, okay, the object is this tall, the image is shorter, right? So you're gonna see the image smaller than the object. Where in this case, if we go back to here, the diagram is not drawn super well, but if drawn carefully, the object and the image gonna have the same size. So same size means that the size of the object is the same as the image. So in terms of the magnification, it's gonna be just 1. So same scaling, no enlargement or no kind of like getting smaller. Where in this case, the image is larger than the object. This is what we get magnification. Okay, so there's one kind of simple formula that we can use. I'm gonna write it down here. Is if we want to find the magnification, M is defined to be the image size divided by the object size. And let's put the absolute sign because we don't need to worry about the negative, the minus sign somewhere here. Okay. So, like again, here the image is smaller than the object, so the magnification is less than 1. So it can be shown, not that simple, but it can be shown that the magnification which is defined this way is actually equal to the absolute value of the image distance divided by the object distance, like this. So in other words, due to the magic of geometry, if you will, the size of the image depends on how far away it is from the lens. So for this particular case here, what is the magnification? Well, the magnification is the absolute sign of SI, which is minus 13.3 centimeters, divided by the SO, which is the object distance. In this case, it's 40. So you can see that the magnification is less than 1. It's about 0.33, right? So the image shrinks compared to the object. Right. So this might not be good as a magnifier because we want it the other way around. So if we go back to the case here, okay, so let's try to calculate the magnification. Well, the magnification is again M equal to minus, sorry, SI, the image distance, divided by SO under an absolute sign, okay? And we put an absolute sign just to get rid of the minus sign here. So what is SI? SI is minus 20 centimeters. SO is 10 centimeters in this case. So the magnification is 2. So you have enlargement. The object is, the image is double the size of the object. Okay. So in terms of our brain perception, you're gonna see the image twice as big compared to the object. So this is how a simple magnifying glass works. Okay, so we can look at this magnification M here. So this is a simple example of the calculation. We can also go back here, but this one is quite not interesting because it's the same for SO and SI, which is 40 divided by 40, so it's 1. So you don't have any magnification, right? So the size of the image is exactly the same size as the object. So there's no magnification in this case. All right? So, you can play a lot around with, like the position of the object what type of lens you use. And you know, a very sophisticated object like the lens for DSLR is just a lot of lenses combined together to give the effect that you want. Right? So in reality, you have to worry about like many things that you ignore. For example, um, you know, the lens itself is not really thin, so it's a thick lens. No, we need to worry about the size of the lens also. But the underlying fundamental physical principle is the same. Okay, so the lens changed the way light travel, and we just use that to our advantage here. Okay, so it's quite a lot to digest for today. So I suggest that you go back and then look through the note or the lecture video again. All right, and on Monday, I will cover the two other cases, which is convex mirror and concave mirrors. Again, it's gonna be mostly repeat of the lenses that we talk about here. And then we're gonna talk about the last topic, which is the diffraction and interference of light wave. And that's gonna be it for the midterm. So all of that will be covered on Monday. All right? So, yeah. The object size, yeah. So for example, if you talk about like the tree, then it's the image of the tree somewhere divided by the size of the actual tree. That's the definition here. But it turns out that it's the same as the distance from the object and the distance of the object to the lens and distance. Yeah, we can use the last one because usually the object size and the image size are not given in the problem. Right, so the last one is probably the one that we use more often. All right. Okay, so that's it for today. If you have any other question, you can leave it on the message. If not, then I will see you on Monday, and have a good day and have a great remaining weekend, everyone. All right, see you on Monday. Take care.